Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for double integrals over simple polar regions. Once you know to integrate double integrals over polar rectangles, then we have a natural extension to simple regions in polar coordinates. First, let us recall what was a simple region in rectangular coordinates. A simple region in rectangular coordinates, it's either a type 1 region or an X region if x moves between two numbers and y moves between two continuous functions that depend on x. And the thing that we end up with is, if that was the case, then the double integral was just an iterated integral in which we put the functions inside. In a type 2 region or a y region, we do exactly the same thing. Now, the y is the one that moves between two constant values, and the x moves between two continuous functions that depend on y. And again, in this case, it's also going to be an iterated integral, only being careful that the limits of integration that have functions go inside. So what's a simple region in polar coordinates? Is going to be more or less the same, something that looks like a simple region in polar coordinates. So if all the points in polar coordinates such that the angle is going to be between two constant angles and the radius is going to move between two functions that depend on the angle. You can also have the other way around, but we're not going to use them in class, so I'm just going to keep it this one. So now we have the double integral of the function is just going to be the iterated integral, being careful that your functions go inside and being careful also that your r is there. So notice that the functions always go inside and the extra r is from the coordinate change. And the reason this is like that is because you can treat this region as a type 1 region if you forget that these variables are actually the variables for polar coordinates, and just use the type 1 or type 2 regions. In this case, just type 1. And then the consequence of changing with polar coordinates is going to be extra r. If you see the video of integration in polar rectangles, you will see why that extra r appears. You are taking a different function for the Riemann sums. But let me just return to one example. And that's the only thing that I want you to understand, is how you can use this formula and how you can remember this formula in order to integrate something like this. Well, first of all, we need to express this circle in polar coordinates. I picked this one in particular because it's not an obvious circle, and it's not that obvious that it is a simple region on polar coordinates. So first of all, we need to express this circle in polar coordinates. So in rectangular coordinates, this circle, and let me just change the marker, is described as this. Changing to polar coordinates, the only thing that I'm going to plug in is r equal to cosine of theta as x and r equal to sine of theta as y, and then I am going to start simplifying things. I get up to here, and then it follows that r is equal to cosine of theta. So r equal to cosine of theta is the edge of this disk. So now that we have that, and notice that in this case, these are the lines theta equal to 0, theta equal to pi over 2, and theta equal to minus pi over 2. So notice that we can express this d as follows. So the thing that we have is that theta moves from theta equal to negative pi over 2 and keeps on moving, passing through theta equal to 0 up to you get to theta equal to pi over 2. And the r is moving, is sweeping all the points between r equal to 0 up to you get to the edge of the circle that is given by r equal to cosine of theta. So that's why the r goes from 0 to cosine of theta. So now that we have expressed it like this, we have just to remind ourselves that if you want to do the double integral of that function, the only thing you do is you just take the iterated integral, making sure that you leave the functions inside and making sure that you put an extra r over there. Once you do that, you can just simplify. R squared cosine of theta plus r squared sine of theta is equal to r squared. Then the thing that I am going to do here So the thing that we can do here is you can see that this is a u substitution. You can integrate that to give you this. You can do it on your own. And then you can just plug in r equal to cosine of theta, r equal to 0, and that simplified gives you this. And then when you integrate gives you theta cosine of theta. When you plug in theta equal to pi over 2 and theta equal to minus pi over 2 gives you this. That ends up simplifying to pi. This is the end of the tutorial. Have a nice night.